Hi guys, so before doing the math for standing waves, so we will start with a string here. Could be the string of a violin or the string of a guitar, and it's fixed at both ends. So I would like to do the math for that. But before that, I have found another app for driven oscillations. So I just wanted to share that with you. You see here you have a vertical spring, so it's an oscillator, and you shake it, so it's driven, right? The the frequency, the natural frequency is about 3.16 rad per second. And if you drive it, for example, at 1 rad per second, you're going to get a very small, this is 3. So you shake it. So it's going to shake it with 1 hertz or 1 rad per second, rather. So 1 rad per second is, so you have to divide by 2 pi to get in hertz, but it doesn't matter. So anyway, the frequency will be the same, but the output, the amplitude that you get here will be very small, right? So let's see, you shake, the shaking is done at that frequency, the frequency of the driver, but you see the amplitude is very small. So I'm going to get closer here. So I'm going to reset, I'm going to put that at 2. So I'm getting closer to the natural frequency. So now I am here, and you see the amplitude get larger, and it's still shaking at the same frequency as the driver, right? But look now what's going to happen if I decide to set the frequency here at the frequency of the natural frequency, right? So can reset. So here I want to do 3.16. Okay, so that's natural frequency. Let's see what's going to happen. You see the amplitude is going to start to increases. I am at that frequency, increases, and then everything breaks, right? It goes so high, so crazy. So that's what we call resonance. And it says resonance disaster simulation no longer realistic. So I thought that's a cool simulation. The other thing I wanted to show you how a standing wave comes to be. And it comes to be because of something we call interference. So it means when you have two waves. So let's see if I can find the simulation. See, you have two waves, and one coming in one direction, the other one coming in the opposite direction. Both waves, they're going to interfere with each other, and sometimes they're going to be destroying each other, and sometimes they will be reinforcing each other. So these are called standing waves. And let me show you. Same website. Have a very nice app to show you that. So that's my string that you excite at its natural frequency, right? So let's say the fundamental, or maybe a higher mode. So it's going to vibrate at a given frequency. And let's see what's going to happen. You see the wave comes in. Of course, this is very slow. It's supposed to be much faster. So you have your wave, and we will study wave after this unit. But it could be a rope, for example, that you shake. So you're going to make a wave. You're going to make a cosine wave here, and it's going to be reflected. Okay, so that will be the reflected wave in blue. So both waves, the incident wave and the reflected wave, are going to interact with each other, and that's how you get a standing wave, right? But I think it's easier to introduce standing wave by introducing natural frequency. So in black here, that's what you see, even though it's a superposition with two waves interfering with each other. So I have yet another simulation. Let's see if I have a wave on a string. You see if you oscillate, you get a standing wave if you oscillate that at the right frequency. So 1.5 hertz, that's going to be one of the natural frequency of the string. Okay, so we will get back to that later on. So let's before we do the math, I just wanted to explain again when you are making music. So for example, if you have a guitar and you plug the guitar, or if you have a bow and you play violin, okay, you expose the violin to a bunch of natural frequencies, and the violin is going to take the natural frequency it lacks in a special cocktail, right? So here you have a guitar, and you see that you're going to have that much of the fundamental, and then that will be the second harmonic, so the second natural frequency, the third natural frequency, the fourth, the five, the six, and the seven. So when you are playing an instrument, unless you really look for the fundamental, or you look for the second natural frequency or the third, you have a mix of everything. So the cocktail that you get, okay, that will make the special tone quality of the instrument, of the timbre. Now, your ear will only detect the pitch, and the pitch will be the fundamental. So I found a very good website to explain that even better. So in that website, they show you a violin, and the violin is playing a note, and I forgot which note it's playing. Let's see. I think here, it's a very good website okay. So the pitch is the B above concert A. So I'm not doing music. I'm not sure what the sounds like, but it's a pitch, right? So the frequency is 497 hertz. So you play that on a violin, and when you use what is called a spectrum analyzer, okay, so you can extract from the sound that you hear, so that B, not B, you can extract all the harmonics. It's inside that sound that you hear. The pitch will be given by the first harmonic or the fundamental, but inside that sound that you hear, you have a superposition of all those harmonics there. So not much of the 10 harmonics, a lot of the one, a little bit less on the two. So it looks like this as a waveform. Okay, you see that it's a superposition of all those harmonics here. And you can, that means the idea is you take all those harmonics here, you combine them together linearly, each one has a special weight, and that will make the sound that you hear. But the most important one, the one that will make the pitch, is the first fundamental here, the first one. So we discussed that last time, but that website is great because you can see, you're going to hear it. So the recording here is a violin, and the pitch is B above concert A. So if you are a good musician, you can hear the pitch, but everyone can hear that it's a violin and it's not a trumpet, right? You can tell the difference. Now, if you look at the waveform, that's what you get, okay? So it's a superposition of many natural frequency, many natural modes. Okay? Now, if you use a spectrum analyzer, that's what you get. So the first one is 497 hertz, which is the note B. The second one will be twice that much. The third third one will be 3 times the first, the fourth one will be 4 times the first, and so forth and so on. But the pitch is just the fundamental. It's just this one. So this is the amplitude, and the unit is decibel. So we will learn about decibel later, but it doesn't matter right now. Now, all those harmonics here will make the tone quality of the violin, but the pitch will be only this one. Okay, so when you use your bow, the violin will pick all the natural frequency it likes, and the first one will be the pitch. Now, if okay, so in this one, what they do, they're gonna put the first harmonic first, and then they add the second, and then they add the third, and then they add the fourth to have the total, the whole sound. Okay, so it means they're gonna play this one. They remove all that. You can do that electronically by using filter, right? So they're gonna get rid of all those frequency and keep this one, and then they're gonna add that one, and then they're adding this one, and then they add that one. So that I thought that was very interesting. So let's see what you get. So first, second, third, fourth, fifth, sixth, seventh, eighth, and they keep adding the harmonics until they get the violent, the all violent sound at the end. So at the end, it's when you have all the harmonics together. So here they have a trumpet. So you see, it's the same pitch. It's the same pitch, but it's not the same cocktail of harmonics, right? So you can compare that to violin. It doesn't sound the same, even though the pitch is the same. So what they did next, they kill all the harmonics for the trumpet or on the violin and just kept the first harmonic. So they remove all the overtones. When they do that, they sound very similar. And that means this means that it's the overtones that make the tone quality of the music. So if you take your violin here and you remove all those overtones and you just keep the first one, okay, that will give you the pitch, it will be very hard to tell apart a violin from a trumpet. So let's hear. So first harmonic for the violin, first harmonic for the trumpet. Okay, it's identical. So I don't know about that website, but it sounds interesting to me. Okay, so next, what I want to tell you. Okay, let's find out if you have. Let's try to find out the relationship. So you have a string. So the length of the string is given. So it could be a violin or a guitar string, and you want to find out the relationship between the frequency and the harmonics number. So let's see if we can do that. So the first one, so the length is given. So the length is L. Okay. And then you have the speed of sound, V. And the speed is always distance divided by time. So the speed of a wave is always the wavelength times divided by the period, okay? Distance divided by time, which is equals to the wavelength times the frequency. So what's a wavelength? If you look at a wave, so you take a snapshot, let's say you have a wave here, take a snapshot at a given time, the wavelength is just the size of the cycle. So that's going to be the wavelength. So this is here, that will be half of the wavelength. And here it's going to be 1/4 of a wavelength. Okay? So the speed of the wave is the wavelength times the frequency, which means that the frequency is the speed of the wave divided by the wavelength. The speed of a wave on the string depends on two things. It depends on the tension on the string, and it depends on the mass per unit length. So the unit here is kilogram per meters, and the tension is Newton. So the speed of a wave always depends on the restoring force, and it also depends on the mass, right? Because more mass means more inertia. So we'll see that in another class. But if you look back to the wave on the string, you see I can make a wave here, but I can change the tension. So this is low tension, so it's not going to move as fast. High tension, right? Or you can also increase the mass or decrease the mass. So it's not the topic right now, but you see if the mass increases, if the mass increases, the speed decreases. If the speed decreases, the frequency is lower. So if you have a violin, for example, a violin is made of 4 strings, and some strings are thicker than others, right? You have thicker string, thinner string. So for the thicker string, that means you have more mass, more inertia. More inertia means smaller speed. Smaller speed means lower frequency, so lower pitch. So thick string will play lower pitch. You can also change the tension at the end of the guitar. For example, you can increase the tension. So higher tension, higher speed, higher pitch. So anyway, so that's going to be the length. So this is here, that will be called the first harmonic. Okay, so the first harmonic. So that means the lower natural frequency. So it's called for n equals 1. And you see that you have, can you try to find the relationship between L and lambda? How much of a cycle do you have? You see that in that case, you have that lambda equals the length of the string divided by 2. Is that right? No, it's not right. It's the opposite. I might be a tiny bit dyslexic here. It's just the opposite. So it means the length, inside one length, you can place half of a wavelength, right? Half of a cycle. So this is one cycle here. So this is half of a cycle. So this is half of a cycle. Okay. So that means that lambda equals 2L, which means that the frequency is V over 2L. So that will be the lowest frequency, the frequency of the first harmonic, which is also called the fundamental. And that's going to give you the pitch. So when you hear music, like a middle A, for example, it's going to be a mix of many harmonics, and the first one will give you the pitch. So second harmonic, so it's n equals 2. So it's called the second harmonic. Second. Je peux avoir overtone. Okay, so in that case, inside that length here, you can have one cycle. Okay, so you have one length equals one wavelength. Okay, so in that case, the frequency equals V, that's 2L. V over L. Okay, so that will be the second frequency. So from how do you go from here to there? You multiply by 2. Okay, so the third one, N equals 3, which is called the third harmonics or the third overtone. Now you can place inside one cycle and a half. So that will 3 over 2 cycle. So lambda. So that means the length equals 3 over 2 lambda, which means that lambda equals 2L over 3. So the frequency equals V times 3 over 2L. So can you see the pattern here? You see that the frequency will be equals to, you always have a V here, and you have a 2L, and then you have an N, and N equals 1 or 2 or 3, and so forth and so on. If you look at the wavelength, it's going to be the opposite. That's 2L. I don't know how I end up doing those L like that. V over 2L. So lambda will be 2L over N, and N equals 1, 2, and 3. Okay? That's correct. Let's see if we get the same thing here in my slides. So here you see the first harmonics will be half of wavelength. Second harmonics will be 1 wavelength. Third harmonic will be 3 half of a wavelength. And then it will be 4 half of a wavelength, and so forth and so on. So that's going to be the equations for a string that is fixed at both ends. Okay, so let's do some exercise now. Let's try, so you can pause the video. Okay. Okay, you have a string support a standing wave with a total of 5 nodes. So let's make the nodes 1, 2, 3, 4, 5. So between the nodes, of course, you're going to have the antinodes. Okay, I don't know if you have the simulation again. Tension low damping. So those points here that are not moving, they are called nodes. So you don't count this part here because this part is the driver. So here you have 1 node, 2 node, 3 node, 4 nodes, but you have 1 antinode, 2 antinode, 3 antinode. So that's going to be 1, 2, 3, the third harmonics. And you just saw that, by the way, I should have insisted on that, but you have the first harmonic F1. The second harmonic will be 2 times F1. The third harmonic will be 3 times F1. The fourth harmonic will be 4 times F1, and so forth, and so on, right? Because the equation is, the first one is, what is it already? It's a V over 2L. The second one is twice that. So it's going to be 2V over 2L, which is V over L. The third one is 3V over 2L. The fourth one is 4V over 2L. So each time here, we multiply by 2, so that will be 1 octave, multiply by 3, and we multiply by 4, and so forth, and so on. So in that case here, so you don't count this. This you don't count. But you see that the frequency here, the frequency is 1.5 hertz, and 1, 2, 3, I am on the third harmonics. Okay? So we divide by 3. That means the first one is at 0.5 hertz. The second one will be at multiplied by 2, so that will be 1 hertz. The third one will be 1.5. The fourth one will be multiplied by 4, so it's going to be 2 hertz. And so forth and so on, right? So if I go to a frequency of, if I go to a frequency of 2, about 2 here, so you don't count this one. 1, 2, 3, should be 4. No. Oh, that becomes crazy, right? So 2, what did we say? It's the 2 hertz, 2 hertz, the 4. So 2 hertz will be the fourth, right? So it's going to be 1, 2, 3, 4. And you don't count that part here. So with this simulation, you have to be careful. You do not count this part here. It starts from here where the bead is not moving, because this is part of the driver. And then you have 2.5. So if I go to 2.5, you get the fifth harmonics. So you don't count. This one doesn't count. You see, you start from here. So it's fixed at both ends. 1, 2, 3, 4, 5. Okay. So let's go back to our business. We were here. Okay, so 5 notes, but you count. So that will be the string before its equilibrium position. And now you have 1, 2, 3, 4. So that's been n equals 4. So that will be the fourth harmonic. So the harmonic number is 4, and the wavelength equals 2L divided by 4, right? So you remember that because you see here the unit for wavelength is meters, and here you have meters, so it's consistent with each other. So the wavelength will be equals to 2 times 12 divided by 4, which is 6 meters. Okay? So let's do this one. So we didn't do waves yet, but I told you that the speed of a wave on a rope, on a string, depends on the tension. You know how tight is the rope, so it's like the restoring force, and the mass per unit length. And actually, I don't need that equation because the speed is given here. So this is V, and the length here is 0.45 meters. So the fundamental F sub 1 equals, so the number is 1 times, so then here you have V, okay, so you have V divided by 2L. And you remember that because look at the unit here. That's going to be meter per second. That's going to be meters. So we cross out. So the unit will be 1/second. And the unit for frequency is 1/seconds because that will be cycles per second. Or also hertz, but it's per second. Okay, so that's going to be equals to the speed 280 divided by 2 times 0.45. Okay, and you get, I forgot my calculator over there. Okay, I think you got 311 hertz. So that will be the fundamental. Okay, so these are very basics. Okay, so this one you are just applying the equation, but once you understand, even the equations are not hard to remember. So the longest wave, right? So this is the first one, and then that will be the second one, and that's going to be the third one, and then you have to be better than me. 1, 2, 3, 4. Right? So the first one will be the longest, will be 2L over 1. So meters, we go it, right? So that's going to be 120 centimeters. And then the next one will be 2L over 2. So each time you divide by the harmonics number, so that's going to be divided by 2. That's going to be 60. And then the third one will be 2L divided by 3, which is 40, right? And then the fourth one will be 2L divided by 4, which is 30 centimeters. And the next one, see, I do the next one. Frequencies. So they want the frequencies now. The speed is given. So speed equals 240 centimeter per second. And I don't know why it says longest, but let's say we compute the first frequencies, the four frequencies, the four fundamentals, and the four harmonics. I think that's what I meant. So length is what, 60 centimeter, and the speed is 240 centimeter per second. Is that centimeter? No, here it's a meters. So here you have to convert that to meters. So the fundamental, it's going to be, you want the 2L here and you want the speed there. So that way you have 1/2. So it's going to be 240 divided by 2 times 0.6. So the first one is going to be 200 hertz. The second one, you don't need to compute because you multiply by 2, which is 400 hertz. The third one is going to be 600 hertz. And the fourth one is 800 hertz. And it keeps going. There is an infinite number of harmonics that you can fit on a string. But of course, when you are playing music, it's really the first ones. Like if you're looking for a violin, after the 10 one, you don't hear anything. I mean, there is no more, right? Even though there is, in theory, infinite number of harmonics. Okay, so here it's the same thing. The frequency is the speed divided by the wavelength, and they call that the speed of sound, which is misleading because C usually is the speed of light, but it doesn't matter. So this one is fundamental, first harmonic, second harmonic, third, fourth, 5, and 6 for the same length of string. So what do you think is going to happen if you are playing an electric guitar? I think it's an electric guitar. And you see, you put your finger here. So you decrease the length by 2. So what's going to happen to the frequency if you decrease the length? So if the length goes down, the pitch goes up. So it will be higher pitch. Longer is the string, then longer is the pitch, lower is the frequency. So low frequency means larger length. And actually, it's also true for music instruments with wind. So the shorter the length here, if this one is small, then the frequency will be higher. Longer means lower frequency. And this is true also for wind instruments. So I have a demo and I will show you where it comes from. And it's true also for organ pipes here. So I'm going to skip a
Okay, this is a demonstration.
Let's skip here.
What we were modes here force different modes to sound in the pipe. What we were hearing just then is the fundamental mode, the lowest possible frequency that this pipe will produce.
So you see, if you heard that, the pitch is very high because this is very small. It has a very small length, and you're going to compare to that one.
But any pipe actually produces a sequence of frequencies that follow at least approximately the harmonic series. So this is the fundamental, the lowest possible frequency. If I blow a little harder, I get a mode that's, for those of you that have a musical background, will recognize as approximately an octave above it. Do the same thing on this one.
So can you see the difference? You can really hear it, right? So the longer one has lower frequency as a fundamental, for the fundamental.
So we get a lower mode, a higher mode, and then there's actually an infinite sequence of these modes that goes up to infinity, and that gives the organ pipe its character, its characteristic sound. As I mentioned before, all of these pipes that I've shown you so far are open on both ends. If you ask what happens when you close one end, and I'm just going to put my hand across it to close this end, then, well, first I'll do it with it open, then close it. So you'll notice that the sound is lower. In fact, if you ignore end effects, then the theory predicts that the sound is actually 1 octave lower, the frequency being half of its original value. That is the reason why a clarinet sounds lower than a flute does. Flute and clarinet both have about the same length. The flute is open on both ends, but the clarinet, the mouthpiece end, is effectively closed. And so the lowest notes you can produce on a clarinet are much lower than the notes that you can produce on a flute.
So we will talk about flute and clarinet next lecture. But if it's open on both sides, then you're gonna have a flute. If it's closed at one side of the clarinet because there is a mouthpiece here and it's open there, that's gonna be a clarinet. Clarinet has lower frequency than a flute. We will explain that later. The point of this video is to show you that if you have shorter length here for the same speed of sound, if the length is shorter, then you're gonna have higher pitch. If the length is longer, you have lower pitch. Okay, so just to show you that video comes from that website here. It's called Physics Demos. And he uses the same book that I'm using. It's called Johnson and Connell Physics. And you can find very nice videos and very nice tutorials as well. So let's finish. Yeah, I think we are almost finished for today. Okay. Okay, let's try to do this one. Okay, so what does it say here? Okay, so that's a linear density. So it means if you have a string here, that will be the mass per unit length. Okay, so that will be the mass per unit length. And as I've told you, like if you have a violin, for example, you have the thicker string and the thinner string. So that will increase the inertia. If the inertia increases, the frequency decreases. So the speed equals the square root of the tension here, which is 2 to 6 divided by the density. So 5 to 8 times 10 to the negative 3. Okay. Okay, so you can plug that in your calculator. So the speed will be 207 meters per second. So find the string between two fixed ends and the fundamental is given. So that's going to be F sub 1 equals, you have the speed at the top over 2 times L. The speed, you just found that it was 207 divided by 2 times L, which L is the unknown, equals to the note E, which is 164.8 over 1. Okay, so you can solve for the length, right? So you have 2L equals 207 divided by 164.8. And whatever you find, divide by 2. and you get 63 centimeter. So the frequency is 164.8 hertz. So now if you want to multiply the frequency by 2, so the frequency is multiplied by 2, so this is multiplied by 2, if this is multiplied by 2, then this one has to divide it by 2, right? So the new length should be the half, so it's going to be 63 divided by 2. So 31.5 centimeters. Okay. So next we're going to talk about those flute and clarinet. And the flute is open at both ends. The clarinet has a mouthpiece and it's closed at one end. So if you want to try for next time, you can do, so that will be the clarinet, that will be the flute. Try to find the harmonics. That means the frequency of the natural, the frequencies, the natural frequencies and the wavelength of the first, the second, the third, the fourth, and the fourth, and the last one. So that's what we're going to do next time. You can also use the website here. Okay, so that will be the flute. The flute is open on both sides. So that will be the first harmonic, the second harmonic, the third harmonics. So you see how at the end it can move. It's not fixed, but you're gonna get the same equation. The equation will be the same as for the guitar and the violin. Okay, so we'll see that next time.